Hello everyone, I am Indrajyoti Gaine, and presently I am a PhD scholar at Department of Mathematics and Statistics IIT Kanpur. Right now I am a PMRF fellow. Before that I was a CSR fellow and I have cleared my CSR net with 108 rank. So today's lecture is about permutation and combination, and we were discussing from the last classes about the permutation and combination. So in the last class we have discussed about the fact that how you can use the factorial notation, and what at first we came to know about what is factorial and how we can write a factorial, what we understand by the notion factorial. And after that we have used this factorial notation to write how the formula for permutation. Okay, and after that we have deduced some formula and discussed some example, and then we have started discussion about the case when permutation of all the objects, when all the objects are not distinct. So for that we have took an example of the word good, where O is repeated once. Okay, so O was appearing twice in this word, and we have discussed how we can consider that 2O and arrangement of that 2O as a single permutation, and how we can compute the number of total distinct permutation. So after that we have discussed the formula for this counting this number of permutation, and we have ended the previous lecture at the point that by stating this theorem. So what is the statement of the theorem? That the number of permutation of n objects, where p1 objects are of one kind, p2 objects of a second kind, and so on, and ending at pk objects are of kth kind, then the number of permutation will be n factorial by p1 factorial, p2 factorial, and so on, pk factorial. And before that we have discussed an example for the word institute. Here you can see that I was repeating twice and T was repeating 3 times. And how we have find the number of total distinct permutation, and we have told that I have told that I will discuss this example in today's class, so that you can understand it properly. Okay, so for that let's take the example again. So let us start today by taking an different example. So I will not consider any word, just take like for 5 words: P, P, O, O, O. So here P is repeating twice, 2 times, and O is repeating 3 times. Fine. Now we need to find number of permutation obtaining from these words without considering with considering the repetition. That is, here repetition it doesn't matter. So number of permutation we need to find. Okay. Now check something. We already know about the example good. So we knew that for the example of good, if these 2 words are different for permutation, these 2 words are different for permutation, but in case of repeated element, where 2 elements are indistinguishable, we consider these 2 elements as a same element, that is good. So for that we were dividing by 2 factorial to reduce that many cases, that many distinct cases. Because for each choice of G and D, and each position of G, D, and for twice O, we are getting 2 factorial extra cases. So just by dividing 2 factorial, we can reduce the total number of cases, and we can get the actual number of distinct cases. Okay. Now, today we have PPOOO. So obviously, for each position of PP, there are two choices. I mean, each position of PPOOO, we have two choices for P, like P, sorry, P, P, O, 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 and the position like this: P, P, O, O, O. So these two cases are same. These two are same case. Again, for these two PPOO, we get three extra cases, right? And these three cases are equally same. What are those cases? First case is, for this case, I will keep the P and blue P and red P fixed. Okay, here blue P and red P are fixed, because for fixed P and PP, we are finding how many different O I can have. So here PP are fixed. Now we are finding for the O. So here first, here second, here third, here second, here third, here first, here last, here second, first, and here second. Okay. Observe that all are same. Similarly, if I go with the case here, same case we will find O, 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 O. These three are same. Okay. So first we have seen that two factorial cases for each permutation, for each choice of permutation, there are two factorial same cases, and for each two factorial cases, I mean for each case of that two factorial case, three factorial more cases are there which are same. Okay. But also you can think of like this, that you can take the permutation for O, like different permutations for O, and you can consider the permutations for P later, and you can check that for each case of three factorial cases, you have two factorial extra cases. So in together, from this observation, from this observation, one can say that here we will obtain 2 factorial multiplied by 3 factorial extra not this many, this time. We should write 2 factorial into 3 factorial times extra cases. 2 factorial into 3 factorial times means I will multiply this. I mean extra, I am extra multiplying 2 factorial into 3 factorial. So to get the actual number of permutation, we need to divide by this number. So what will be the actual number of permutation? Hence, actual number of permutation is 5 factorial divided by 2 factorial into 3 factorial. Okay, so this is the actual number of permutations. Okay, for this case, we have this many permutations which are distinct. We can distinguishable, we can say, because these three elements or these two elements are not distinguishable. What we have discussed for this example good. Okay. So thus we can get the number of distinct permutation for the case where all the elements are not distinct. So by this process, one can prove for k elements by induction. One can prove the repetition for k elements, and they can obtain this theorem we have stated in the last class. So let us state the theorem again today. I hope you are clear about the proof of this theorem. You can repeat these steps again and again, and after by kth element, or you can say by induction hypothesis, one can prove this theorem. The number of permutation of n objects where P1 many objects are of first kind, P2 many are of second kind, and so on, and ending at pk many at pk many of third kind. Then the formula of the number of permutation will be n factorial divided by p1 factorial, p2 factorial, and so on by pk factorial. Now one can ask that what is the assurance that this repetition number, that is pk, are of third kind, sorry, not of third kind, this will be of kth kind. Kth kind. So what is the assurance that this repetition will be stopped at some point? It may happen that pk plus 1 is of k plus 1 kind, and pk plus 2 is of k plus 2 kind, and so on. It is going on. It's not ending at some point. It is not possible because the number of objects is finite, that is given by n. So we can't get unlimited number of this many repetitions and all these things. Okay. So let us do one example using these things. So let us do one first example for the permutation cases. The question is, how many numbers lying between 100 and 1000 can be formed with the digits 0, 1, 2, 3, 4, 5 if the repetition of the digits is not allowed. So what is the question? How many numbers lying between 100 and 1000, that is in between 3-digit numbers, can be formed with the digits 0, 1, 2, 3, 4, 5. Now, first observe few things, that what are the numbers between I mean, what are the numbers we can form without repetition by these numbers, by these digits, which are lying between 100 and 1000. So if I write this, okay, like the numbers are like of the form 102, 204, 105, 501. Here we will not include 500 or 511 or 344. This kind of numbers will not be allowed here. This kind of numbers will not be allowed in this case. We can't allow because here one digit is repeating. So this is not allowed. The repetition will not be allowed here. Okay. So this kind of number will be included in this range. Fine. Now the question is how many numbers I can then count. So we can take the help from permutation, right? So the number of permutation. So the number of permutation will be is, so what will be the value of NPR? We should use the formula NPR, right? So what is the N here? N is here 6. Here N is, so the number of permutation. Okay, take this. So here N equals to 6. Why N equals to 6? Because we have only 3 digits. Sorry, 6 digits. Okay, so I can only choose only these digits to write any number between 100 to 1000. Here we can't use 6, can't use 7, 8, 9, and so these things. We can only allow to use these digits. But here I can see only 6 digits are left. I've given here. Now one can ask that if I replace 5 by 6, or if I replace these 6 digits by 1, 2, 3, 4, 5, 6, so will it be the same concept? The answer is yes. Concept will be more or less same, but here something is tricky. So let us do the example for 1, 2, 3, 4, 5, 6 first. Then it will be better to go with 0. There will be some twist for the case with 0. So here you can see that only 6 digits we have. So here n equals to 6. Okay? Because we have 6 many digits and we can only pick 3 of them and make a number. Why? Because 3 of number, because in between 100 and 1000 we can have only 3 digit numbers without repetition. If it is repetition is allowed, then 1000 is also allowed if 0 is included here. But here repetition is not allowed, therefore only I can go up to 3 digit numbers. Okay. So here R equals to 3. Then what will be the formula for permutation? So it is denoted by the cardinality of permutations will be 6p3, which will be the 6 factorial divided by 6 minus 3 factorial, which will give us 6 factorial divided by 3 factorial, which will again give us 6 into 5 into 4, 120. Okay. Okay. Now this is this many numbers I can get in between 100 and 1000 using 6 digits. So here I can use the other digits instead of 1, 2, 3, 4, 5, 6, and you can take any non-zero digit to get this number. Right? But what is the difference if I include 0 here? In place of 6, if I write 0, what will be the problem? So in case of non-zero digits, all the elements, all the combinations with this many digits are allowed to stay inside 100 and 1000. But in the case of 0, where 0 is one digit and 0 is allowed, then we can't include these words like 0, 1, 2, 0, 4, 5, 0, 5, 3. So this will not be allowed in the case with 0. Why it is not allowed? Because these are less than 100. Okay, but whenever we are counting the permutation by this formula, we are also including these numbers, because we are not treating 0 as some special case. We are treating 0 as a particular digit, and we are considering that here we have only 6 digit, and we can take three many digits from this 6 digit, and we can do all the permutations and all those things. So here we are considering this many extra cases. So we need to eliminate this many extra cases. Now, don't get confused with the previous example that when the words were repeating and we were just dividing by 2 factorial or 3 factorial things, because in the previous examples we were written this, we have obtained 2 factorial into 3 factorial times extra permutation. This times, because for all possible permutations, we are getting 2 factorial into 3 factorial extra cases. Okay, so in case of this, we have already multiplied 2 factorial into 3 factorial extra cases. So for to reduce that many cases, we need to divide by 2 factorial into 3 factorial. But here, but here we have extra cases which are not like that. For each choice of other two number, we have that many extra cases. We have only that many extra cases. So how many extra cases we can have? So in the case of that, we have 3-digit numbers, right? So in the first case, we had choices for all the places, right? For this, I had 6. For this, 5. This, I had 4. I am not using the formula. I have used a formula here. But in general, if I go with the concept, background concept, then we can write that there are this many cases, right? But I am eliminating those cases where 0 is in the first place. Okay? So I am fixing the first element. Fixed now. So how many cases we will left with? So I have now only 5 digits and only 2 boxes. So in that case, I will have 5 into 4. Correct? 5 into 4. Because we have only left with too many boxes, and we have only 5 digits. So we can put the first box with the 5 elements, and we can have only left with 4 elements for the second box. So the case will be 5 into 4. So that many extra case I have. So in term of permutation, what will be the case then? So this can be written as 5p2. Why 5p2? Because first element is fixed. So we are not considering 0 as an digit. We are left with only 5 digits. We are left with only 2 places. We are just finding all possible permutations. Okay. Now we are eliminating this blue case to obtain the exact number for this case. We should eliminate the blue case. Sorry. The blue case from the red case. So the number will be 6 P3 minus five P2, which will be the number 120 minus 20, which will give us 100. Why 120? 120 because this red will give us 120 and this blue will give us 20. So this is the example, and we have to understand that what is the logic or what is the demand of the question, and why this, how to again use the permutation formulas to get the answer. Now one can ask that here the repetition is allowed or not allowed, because repetition is not allowed is already stated in the first. Now if I just say that repetition is not allowed, and I have given one extra digit like 1 here, like 1 I have given twice for this case. So even though repetition is not allowed, but 1 is appearing twice, so for 1 I am getting 2 factorial times extra cases. So that I need to eliminate, even though repetition is not allowed. Okay, so that's how we will manage the questions, and you have to understand the question and what is the uh, inner meaning of that question to get the answer properly. And you have to choose that how you should, what should you use, and what you should not use. Which formula should you use? Which formula you should not use? That things. Okay. So let us do another example. The example is, find the number of different 8-letter arrangement that can be made from from the letters of the word BAUGH daughter. Okay, if when the arrangement that can be made from the letters of the word daughter, first case is when all vowels occur together when all vowels do not occur together. Okay. So how many vowels first? Identify that how many vowels it has. Let us write this word daughter again. EHTER. And we need to find the all possible permutation where the vowels are appearing at the together. Together. Why together means that it will not come like vowels are, there will be no gap. There will be no gap of word. Like how? Here are the vowels A, E, and U. So we have only 3 vowels. Fine. Now these vowels will appear together. Okay. So we have only 3 vowels. and these vowels will appear together in the first case. So in the first case, we can think these vowels as together. Like here, you can see that the vowels are not appearing together. A, U, and E. There are some gap between, and in that gap there is G, H, and D. This is not allowed in the first case. Like what can happen? Like this can happen here. D, A, U, E, G, H, T, R. You can see that these three words appear together. Or it can be happen like D, E, A, U, G, H, T, E, R. So you can see these three appear together. Or also it can happen like D, U, A, E, G, H, T, E, R. This is also allowed. Okay. Now also this can happen D, G, U, A, E, H, T, E, R. You can see again that these three appear together. Also for this, we can get again of this form A, U, E together, H, T, E, R. Fine. So you can see that this many cases again, and this all I mean, there are more cases, but these are the cases, this type of cases I can get. Okay. So in the first case, the vowels will appear together. This means that vowels will appear like this. Fine. Now just count first that how many words or how many letters this word have. 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 letters, but here 3 letters appearing together. For the first case I am discussing, 3 letters appearing together. So we will consider this 3 letter as one letter. Okay. Here we have 8 letters, but among them we will consider 3 letters as a one letter. So we are left with only 6 letters. How? Because 8 minus 3 equals to 5 and plus 1. Why? Because we are considering these 3 letters as one letter. So here we are left with 6 letters. Now, how many ways one can write these 6 many letters? That will be 6 factorial. Right? Because we are writing 6 many words in 6 choosing 6 words at a time from 6 many letters. So this will be 6 factorial because 6 is 6 and it will be nothing but 6 factorial. Fine. Now, for each choice of this 6 factorial, we are getting 3 factorial extra cases. Why? Because you can see that if I write this as red, this as white, and this as blue, you can see that others are same, but the ordering of A, E, and U are getting exchanged. And how many possible exchange we can get for one particular other places of when other places are fixed, we can get 3 factorial extra cases. So for each choice of the 6 factorial cases, we will get 3 factorial extra case depending on the arrangement of these 3 vowels. So for that, we will multiply this 6 factorial by 3 factorial to obtain actual number. I am not calculating the actual value, but yes, you can understand the you can calculate the value from here. So this is the exact number of the cases when all vowels occurring together. Now, what about the second case? When all vowels do not occur together. So for that, you need to what you need to find. You already have find that when all vowels occur together. So if you eliminate those cases from the actual cases, then you are done. What is the actual case? Actual case is 8 factorial, because here we have 8 many words and we can write 8 factorial distinct words depending upon by choosing these elements, because we have 8 many letters and I am choosing 8 many letters from 8 many objects. I'm just like 8C8, and we are getting 8 factorial different cases of writing this writing some word without meaning or with meaning using these letters. Among them, we already know that 6 factorial into 3 factorial cases are together. That is in that those cases I will eliminate from the main cases. So we are left with only this many cases. 8 factorial minus 6 factorial into, sorry, and we should write properly here in small font. 8 factorial minus 6 factorial into 3 factorial. Fine. So this is the exact number. This many numbers I can have when all vowels do not occur together. Okay. So thus we can find many cases. For example, I can take another example here. So question is, how many ways can 4 red, 3 yellow, 2 green discs can be arranged in a row if the discs of the same color are indistinguishable. Indistinguishable. So how many ways can 4 red, 3 yellow, and 2 green discs and can be arranged in a row of the if the discs of the same color are indistinguishable? So obvious thing, that is 4 red. Now if I name it by first red, second red, third red, fourth red, then this will not matter that which red is coming in the first. So this is the case where repetition is the case for this thing, where the colors are getting repeated and they are not indistinguishable. So how many cases I can have from this formula I can get? So what is the total case? Total case is here 4 plus 3 plus 2. So here n equals to 4 plus 3 plus 2. This equals to 9, right? And what will be the P1? P1 is here 4, because P1 means this many objects are of first kind, means they are of first kind, means here red colors. So P1 many elements are of color red. That is 4 elements are there which have color red. P2 equals to here the color yellow elements, that is 3. That is not element. This is, and what will be the P3? P3 will be 2. So using that formula discussed in the beginning of today's lecture, we can use this formula here. And we can get the answer for the cases, that is 9 factorial divided by 4 factorial, 3 factorial, 2 factorial. Now one can calculate this. So just calculate little bit. So what will get 9 into 8 into 7 into 6 into 5 into 4 factorial divided by 4 factorial into 2 factorial means 2 and 3 factorial means 6. That is divided by 12. Okay. Now 4 factorial can be cut. And here I can say 3 4 is 12. Sorry, no, it's 6 and you can get 2 and 2. 4 is 8. And you can multiply this and you will get the answer 1260. Okay. So this many cases I can obtain by arranging these things. So here I am using the formula for the case where the order is not that much important. Okay. Now, up to this we have discussed about the permutation cases. Now, here repetition is not allowed is a very much important thing that we have discussed, like this good example, and today also we have discussed in the example with institute. And now you can, if you go with the example with institute, you can understand it properly, because here the t was appearing 3 times and I was appearing 2 times, and why we have divided this total number of permutation by this 3 factorial into 2 factorial. Today you can understand properly. Now the thing is, why this permutation when all the objects are not distinct is important. Because today, last day we have discussed, or previous day we have discussed that example of some apples, right? That we have 10 apples and we have 4 cartons, and we have to divide these 10 apples into 4 cartons. Now we can, how many ways there are to divide these elements. Now the thing is, who is getting the first apple and who is getting the second apple, it doesn't matter to them. Or also one can think of like in some school event, boys are standing or girls are standing in a row and distribution of the lozenge is going on. Now who is getting the first lozenge, it doesn't matter. We just need to divide, or we just need to distribute the lozenge among the students. Now how many ways I can distribute this lozenge among the students, that's matter, right? It doesn't matter that Rohim is getting the first lozenge or Rakesh is getting the second lozenge or not. It doesn't matter. So ordering is not that much important in that case. So for that purpose, this kind of thing have appeared, came into the picture, that when the objects are not distinguishable. So also one can think of one example like this. Like this is a circle. Now, how many possible chords? Okay, not like that. Let us fix some points on the circle. 4, 5, 6, 7, 8. Okay, these are the fixed points on this circle. Now, how many possible lines I can draw from these points? So one can draw this line, 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 and so on. One can draw like this line, this line. Okay, that's depend on the person. Now, the important part or the interesting part, you can say that we will consider this as a single line. We will not consider this opposite direction as a different thing. So in that case, if I name it like 1, 2, 3, 4, 5, 6, 7, 8, and if I denote this this straight line like 1, 2, then just understand one thing, that 1, 2 and the blue line 2, 1 are not distinct. These two are not distinct. Why not distinct? Because basically there are two indistinguishable lines. There is no difference among them. So for that, we have discuss this phenomena that when the repetition is not indistinguishable, then they are not distinct, right? So this thing is known as combination. This factor is known as combination. So in case of combination, we are considering the similar kind of object as in one element or as in one cases. Okay. So what is that? Also, one can think of as example like in a big room, 12 people are there and they are shaking hands to the each other, and how many handshake will be there among them? That is also combination. Now we have discussed about permutation. We have discussed about the repetition case. Now, what is the number for permutation? That is how many of this state lines I can obtain from these 8 distinct points? This is the question. So this will be called as combination. So here the comes the combination. Combination. So combination is nothing but permutation plus permutation for distinct objects. Okay. So nothing but that. So by example, I hope you are clear about the concept of combination. Now we will go with how we can get the number of combination for some cases. Okay. So let's do one understanding thing. So for this case, let us understand from here. So we have only 8 points and we are choosing 2 points at a time and drawing a line. So how many possible lines I can have by using permutation? See, using permutation, we know that using permutation, we know that the cases of line, the number of line, that the number of lines number of lines will be 8p2. Perfect. Why 8p2? Because 8 many points I have and we are choosing 2 elements from there. Now what I have discussed that in the permutation case, we are distinguishing these 2 cases. We are considering these 2 cases as 2 distinguished cases, but this is not the case for combination. So we will divide the whole number by 2 factorial. Why 2 factorial? That thing I have discussed today, beginning of the lecture. Because we are getting 2 factorial times extra cases. So to get actual number of distinct cases, we need to divide by 2 factorial. So this is the formula for, you can say this thing we denote as 8C 8C2. This factor we consider as 8C2, sorry. 8C2. And what will be the exact formula? Formula will be 8 factorial divided by 2 factorial into 8 minus 2 factorial. This is the exact formula for 8C2. Now if you replace this by N and R, then you can get NPR. This is nothing but NCR into R factorial. Why this NCR into R factorial? Because we are in the case of combination, we are eliminating R factorial times cases. We are not considering them as distinct case. So we are already eliminated that time elements. So we are multiplying NCR with R factorial to get NPR. That is the permutation. So in case of formula for NCR, we will get NCR equal to nothing but N factorial divided by N minus R factorial. This is the case for permutation. And again, we will divide by R factorial. to obtain the formula for NCR. So thus we obtain the formula for combination, that is how many possible combination we can get from n distinct objects using R at a time. Okay. Okay. So this is also considered as a theorem. You should recall this factor here. Okay. Those are not working properly. So NPR equals to nothing but NCR into R factorial. Okay. Now, what about NC0? And what about NCRN? NC0 is n factorial divided by n minus 0 factorial into 0 factorial. That is n factorial divided by n factorial equals to 1. And what about NCN? It will be n factorial divided by n factorial minus n factorial. That will be given as 1 again. But in the case for permutation, you can understand that n factorial, NPR, NPN was the whole n factorial. But here you can see that this will be 1. Okay. Now let's end today's lecture with the last formulation, that is NCR minus 1 equals to n plus 1 CR. We will derive this formula and we will end today's lecture. And from the next lecture, we will discuss some example regarding these combinations and how you can distinguish that this is the case for combination or this is the case for permutation, and where you should apply which formula, where you can understand which kind of concept to understand the factors. So let's discuss this formulation. So hotel formulation. So let us take with the left hand side NCR minus 1. Formula n factorial divided by R factorial into n minus R factorial plus n factorial divided by R minus 1 factorial minus n minus R plus 1 factorial. Now from here, just understand that among them, this and this, which one is larger? Obviously, larger one is n minus R factorial. Why? Because that was this is a smaller thing, that kind of thing. So here I can write like this. This can be written up like this. Okay. N factorial divided by R factorial can be written as, I am just trying to get these terms here. So how we can obtain that? So if I write like this, R into R minus 1 factorial, which I have already discussed in the factorial notations. We have done this, the n factorial equals to n into n minus 1 factorial. Here I have discussed, right? Yeah. Here I have discussed things like n factorial equals to n minus n into n minus 1 factorial. So I can write R factorial as R into R minus 1 factorial. And similarly, n minus R factorial as n minus R into, okay, sorry, not like there, I am not right here. Okay, n minus R factorial I will keep here, and here I will write R minus 1 factorial and n minus R plus 1 into n minus R factorial, because usually we reduce 1 from the previous term. Perfect. Here I had n minus R plus 1. That can be written as just reduce 1. Just multiply that element and multiply the factorial of one reduced element. like what we have done in the previous lecture, that n factorial equals to n into n minus 1 factorial, right? Now if I replace n by n minus r plus 1 factorial, so that will be nothing but n minus r plus 1 into 1 minus 1 means this 1 will be eliminated, so I will get n minus r factorial. This I will get. Now let us take common. So if I take common, what will get? N factorial divided by r minus 1 factorial n minus r factorial. The first thing I will get 1 minus r plus 1 by n minus r plus 1. Okay. Now do the calculation, proper calculation, nothing else. N divided by r minus 1 factorial real r into n minus 1 r plus 1. Here I will get n minus r plus 1 plus r will be reduced. So ultimately we get n plus 1 into n factorial divided by r into r minus 1 factorial n minus r plus 1 n minus r factorial. So this will give us n plus 1 factorial divided by r factorial into n plus 1 minus r factorial, which will nothing but n plus 1 cr. Okay. So just by calculation, simple calculation, we have obtained this result. We have obtained this result. So from today's lecture, we will discuss, from tomorrow's lecture, from next day, we will discuss some example using all these formulas and where I should use combination and where I should use permutation, and how to distinguish the cases where should I use which example, and how to understand the questions of this kind of example. We will talk about in the next class. So let us finish today here.